now we're going to look at the application of Gauss's law, again using spherical geometry to calculate the electric field from R equals 0 to infinity for a spherical insulator that has the charge, the positive charge, uniformly distributed throughout the surface. So this would be for an insulator, or if they were negatives and it was the electron cloud of an atom, we would do the same thing. So uniformly distributed. And in this case, our Roman numeral 1 Gaussian surface. So anywhere, again, it goes anywhere in the limits that we're interested in. So we're going to put it between 0 and capital R, symmetrically placed within the problem. And we now write down Gauss's law, E dot n integral E dot n hat dA equals Q enclosed over epsilon naught. Q enclosed is no longer all of it. So we are always going to first deal with the Q enclosed once we see we have this situation where we do not have all of it. So if we don't have all of it, how much of it do we have? Well, the trick we are going to use to calculate how much of it that we have is to set density equals density. Not very profound, but that's what I want you to be thinking of. So for any uniform charge distribution, uniform means uniform density. Density equals density. So the density of the total amount of charge that we have, the total Q enclosed in the total volume, 4/3 pi r cubed, has to equal the Q enclosed divided by the volume that we have, the volume enclosed. So that is where we get our Q enclosed statement from. So that is where you want to start all of these problems. So let's continue it out then. So now, once we have Q enclosed, we are going to show all of our steps. I'm not numbering them on every page of notes that I have, but all the steps are here, right? So the n hat is shown on my Gaussian surface. It's a positive charge distribution, so the electric field vector is shown. The cosine of 0 degrees then is shown, right? R hat. It's shown in my drawing, so I don't need written justification. It's shown graphically. The Q enclosed I now have, so I'm going to put my Q enclosed, right, in for Q enclosed. So I get that, the Q enclosed divided by epsilon naught. Notice the E comes out of our integral by symmetry always. So we will always be assuming that the symmetry in the problem is going to dictate that the electric field at any point on the surface of our Gaussian surface will be the same. The same for our integration, since we're integrating over that area, means comes out constant on the surface by symmetry. The integral of dA is A, so 4 pi r squared. So hopefully you're beginning to see how this game is going to be played, because it'll be played the same way each and every time. We get an interesting result here, however, because mathematically we have an r squared on the left and an r cubed on the right, so we lose the r squared here totally, and our r cubed goes to an r that we have. So we have a linear electric field increase as we go from the center of this ball out to the surface. So that's why we show this as a linear. E max is when little r equals capital R. And we are done from 0 to R. Now, outside of the ball, I'm not going to continue to show all of the steps that I showed in our last example, but outside of the ball, the Q enclosed is all of it, so it's the identical calculation to what we just showed. The E comes out by symmetry. The integral dA is A, 4 pi r squared, so we get our result that we just showed. Basically, the point particle, the sphere mirrors the point particle. It's a 1 on r squared. And we have that profile here out to infinity. I have everything labeled, so we get these kind of like shark fin type of a profile. And that is it. So if we had shown this earlier on a quiz or a test, we would not have to go back and show all of the steps. You could just say that the steps were shown in a previous problem as they were here, right? So the Roman numeral 2 is the same Roman numeral 2 off of page 12 of our notes to get that profile. So go back here one more time. You can pause the video if you need to get all of your annotations. And we are on our way.